The next chapter that we want to look at, chapter 4, deals with the subject of gravity. And we're also going to look at how projectiles work and then satellites. Now, Isaac Newton discovered that the force of gravity between any two masses is given by the following formula. F, which stands for the force of gravity, is equal to this constant big G. And big G is written down below. It's a very tiny number. It's 6.67 times 10 to the minus 11. And then it's got a bunch of units to make the units work out over here to be newtons. We know the force has to be in newtons. So all of this stuff just multiplies with the units of the other things in the formula so that what you end up with is newtons after everything cancels. But the main thing is that we have this constant, big G, which is 6.67 times 10 to the minus 11. Remember that 10 to the minus 11, what that means is you take the decimal place and you move it over to the left 11 spaces. So it's there'd be 10 zeros and then 667. That is a tiny, tiny number, which kind of tells you that the force of gravity is actually very weak. It's a very weak force because this value G is such a tiny number. But gravity doesn't just depend on G, it also depends on the masses. And so if you take something really, really massive, say like the planet Earth, there's so much mass that little G gets overwhelmed by how much mass you have. But this formula will even work even if the masses are tiny too. There will always be a force of gravity between any two masses. And so it's equal to this number, big G, times whatever mass this one is and whatever mass that one is in kilograms. And then you divide by d squared, where d is the distance between the two masses. And the thing when people use this formula that they tend to forget is to square it. Remember, when you square something, that just means you multiply it by itself. And so d squared means you take the distance between the two masses, multiply it by itself, and that's what you divide by in the fraction. So I've written it down for you that you can write down on your PowerPoint presentation. M1 and M2 are two masses, and d is the distance. Specifically, it's the distance between the two masses. And then, of course, our value F, that's the force of gravity. So that gives us the force of gravity is big G times M1 times M2, the two masses multiplied together times big G, and then you divide it by the square of the distance. This is sometimes called Newton's universal law of gravitation because it applies throughout the whole universe. Any two masses, you and the planet Earth, have a force of gravity between them. You and your next door neighbor have a force of gravity between you. Two asteroids floating in outer space have a gravity force that's attracting them together. So the force of gravity is given by this formula. Let's look at an example. So here is our example. The mass of the Earth is given by M sub E. The E stands for Earth. The mass of the Earth is 5.97 times 10 to the 24 kilograms. Now, 10 to the positive 24 means you take the decimal place and move it to the right 24 times. So that's 597 and then 22 zeros. So the mass of the Earth is a really, really big number. The mass of the moon is 7.35 times 10 to the 22. Now, here you can see 10 to the 22 compared to the 10 to the 24. The moon's got about 100 times less mass than the Earth, but it's still a really, really big number. And so you have the mass of the Earth and the mass of the moon. And then the question says if they are a distance d equals 3.84 times 10 to the 8 meters, what is the force between the Earth and the moon? That is, what is the force of gravity between the Earth and the moon? To answer that, we simply need to plug the numbers in for each of these variables. So we know our big G is this 6.67 times 10 to the minus 11 Newton meter squared per kilogram squared. The mass of the Earth is 5.97 times 10 to the 24th kilograms. That's our M1 here, the mass of the Earth. M2 is going to be the mass of the moon. So that's 7.35 times 10 to the 22 kilograms. And then we divide that by 3.84 times 10 to the 8 meters. All of that gets squared. And when you plug all of those into your calculator, you end up with 19.8 times 10 to the 19 newtons. Now that's a pretty big force, but the Earth and the Moon are pretty big, so they give a pretty big force of gravity between them. Now when you're considering the force of gravity, once you have the two masses, unless one of the masses gets cut in half or something, usually the masses aren't going to change. But what can change is the distance between them. So the force of gravity, if the force of gravity between two masses changes, it's because the distance between the two masses has changed. So it makes sense to ask, how does the force of gravity behave? How does it behave when the distance is changing? And it obeys something called an inverse square law. In other words, the distance goes as the inverse of the square of the distance. Remember, if you look at the force of gravity, it goes as big G, m1, m2, all multiplied together and then divided by the distance squared. So the force actually goes as 1 over d squared because all these other things are constant. And so the distance is generally the thing that changes. So mathematically, what does that mean? It means that if I take the distance and double it, the force actually goes down by a factor of 4 because 1 over 2 squared is equal to 1/4. And if I make the distance 3 times as big, I get 1 over 3 squared, and that gives me 1 over 9 because 3 times 3 is 9. So if I double the distance between the two masses, I get 1/4 of the force. If I triple the distance between the two masses, I get 1/9 of the force. Now what happens if you make the distance half as much? Well, I would get 4 times. If I make it 1/3 as much, I would get 9 times because we're just flipping these over. In other words, if doubling the distance drops the force by 4, halving the distance has to increase the force by 4. And so we can figure out just how much the force changes by how much the distance changes using this relationship. And of course, let me ask you, if I make the distances 4 times as much, how much does the force fall by? It goes to 1/16 as much. And so if I've got two masses and they're a certain distance apart, and then I take those same distances and I make them 4 times the distance apart, I know that the force, the new force after the masses have moved, is 16 times smaller than the force when the masses were closer together. That's what this is telling us. And you can see here in the picture, they've actually graphed the force with distance. So you can see the further away you get, the smaller the force goes. Now, the last thing I want to mention about this, if we look over here on the upper right, we've got this formula for the force of gravity. This is the force of gravity between any two masses separated by any distance apart. Often, we're interested in the force of gravity where we are, on the Earth. Now, the force of gravity depends on the two masses and the distance between them. And actually, if it's something big like the Earth or the Moon, it's the distance between their centers. And so imagine that you're standing right here on the surface of the Earth. The force of gravity is your mass times the mass of the Earth, all times that big G, of course, and then divided by the radius of the Earth squared, because that would be the distance from where you're standing to the center of the Earth. That would be the D. And no matter where you are on the surface of the Earth, that radius is going to be the same because the Earth is basically a sphere, and we know that means the radius is always going to be the same. So what does that tell us? It tells us that the force of gravity acting on you on the Earth isn't going to change as long as you're not leaving the surface of the Earth. And so we can simplify it when we're talking about the force of gravity acting on someone or something at the surface of the Earth. In fact, when someone's at a location like that, we call the force of gravity their weight. And the formula for calculating the weight is much simpler than this formula over here. Because nothing's changing, we can use a different formula to calculate the weight. And remember, weight is just the force due to gravity, but it's the force due to gravity on the Earth. Or it could be the force due to gravity on the Moon or on Mars if you were talking about that. But usually we're talking about the force due to gravity on the Earth. And so Newton's second law tells us that all forces, including the force of gravity, are equal to the mass times their acceleration. And we also know that on the Earth, near the surface of the Earth, the acceleration due to gravity is little g, which we know is 9.8 meters per second squared. And often we say about 10 meters per second squared, but we know it's really 9.8. So if the force of gravity is the mass times the acceleration, and the acceleration is little g, we can call the force of gravity m, the mass, times little g, the acceleration due to gravity. And of course, the force of gravity is the weight. Thus, we have a formula for calculating a person's weight near the surface of the Earth. Now, what if you were on Mars? You'd do exactly the same thing, but you'd have a different number for the acceleration due to gravity on Mars. And I don't know what that number is, but I could probably Google it and look it up if I really needed it. But we're not going to worry about Mars in this class. We're just going to assume that if we're talking about your weight, we're going to be talking about your weight on the Earth. Now, the next thing that we want to talk about is what it means to be weightless, because that's something that's really confusing to people. They think that, they see movies where someone is in a spaceship orbiting the Earth and they're floating around and they say they're weightless. A lot of people think that that means that gravity isn't working in outer space, but that's not true at all, and that's not what weightless means. So when you feel weight, what is it that you actually feel? You're not actually feeling the force of gravity pulling on you. If you were standing on a cliff and you were to step off, gravity would of course pull you down. But why don't you get pulled down when you're standing on the cliff? Because by Newton's third law, the gravity's pulling you into the cliff, but the cliff is pushing back with an equal but opposite force. What you feel is not gravity. You feel the ground pushing back. If you stand on a bathroom scale, you have your weight, which is, of course, we know m times little g, that's your weight, pushing you down into the scale. And you don't go crashing through the scale, again, because Newton's third law tells us that the scale is going to push back with an equal but opposite force. What force? Equal and opposite to your weight. And there's a spring scale inside the scale, or some sensor that's hooked up to a digital meter that's able to measure how much the compression of this scale is and convert it into how much weight is necessary to squeeze it by that much. And so what's actually measured on the bathroom scale is not the weight, but the support force that you're feeling. Now, what happens if you're on a cliff, say in a car, and you drive off the cliff? At that point, you no longer have that support force pushing back on you, and you're weightless. You don't feel the force of gravity anymore because that's what you feel. You feel the support force pushing you back. If you take away that support force, you don't feel anything, and we say that you're weightless. Now, what's going to happen here? The car and you are going to be free falling. And that means that you're both going to be falling at a rate of about 10 meters per second squared. Actually, we know it's 9.8, but we'll call it 10. So here's the thing. Both you and the car are falling at the same rate. So there's nothing to keep you pushed against the seat of the car. If you're in the car on the cliff, gravity's pushing you into the car and it's pushing the car into the cliff. But once you leave the cliff, both of you are falling and you're falling at the same rate. So you'll float, if it's a convertible like this, you would float right out of the car as you were falling. And you've seen skydivers who jump out of planes and they're able to do somersaults and all kinds of things as they're falling because there's no support to stop them from doing that. Now, coincidentally, if you're in space, you have that same kind of feeling because there's no support force to give you the sense of feeling what gravity is acting on. Now, this is a great example of how forces and weight apply inside an elevator. If you've ever ridden in an elevator, and I think most of you have, you know what it's like. You press the button and the elevator starts going upwards and you kind of feel heavier for a second or two. And then you feel normal. And then as the elevator is stopping, you feel lighter. Your stomach kind of drops out a little bit. Why is that? Why does it feel weird in those different ways? It has to do with the fact that during some parts of that motion, the elevator is accelerating. It's changing its velocity, and we know that when anything changes a velocity, when anything accelerates, that means you have to have forces involved, because force equals mass times acceleration. So there are actually 4 different scenarios indicated in this picture, and I want to look at each possible scenario. So the first scenario on the far left is that the acceleration is equal to 0. So there's no acceleration. That means there's no net force. Now, before I go in and talk about force, let's just remind ourselves so that we're very clear about what it means for acceleration to be 0. There's 3 possibilities. It could mean that the elevator is just sitting still. The elevator doors open, you climb in, nothing's moving. If you stand on a bathroom scale in an elevator that's not moving, the bathroom scale is going to read your normal weight, just as if it was on the floor outside the elevator. Now, we also know that A equals to 0 means simply the velocity is not changing. Remember, acceleration is change in velocity over change in time. If the acceleration is 0, that means the change in velocity is 0. In other words, the velocity ain't changing. It's constant. So, if the velocity is constant, either going up or going down, or has a constant velocity of 0, not moving at all, the acceleration is 0, and in all of those cases, you're going to read your normal weight. But what if the acceleration is not 0? Well, here we have some other scenarios with different accelerations. One, we have an acceleration that is upwards. In that case, there's a cable that's pulling the elevator upwards and it's causing it to change its velocity. It's accelerating. The bottom of the elevator has to push on you to accelerate you with the elevator. And so what's going to happen is the scale reading is going to increase because it's got to push with enough force to hold your weight up, and then it has to push with an additional force to accelerate you, because for you to be accelerated takes a force too. And so the bathroom scale reading, if the elevator is accelerating upwards, it's going to be a greater reading. And during the time when the elevator is accelerating upwards, you're going to feel heavier. You feel an increase in weight. We call that your apparent weight. You're not really heavier. You haven't eaten a bunch of food and gained a bunch of mass and gotten heavier. You're just feeling heavier because of the acceleration. It's the apparent weight, not the actual weight. Now, the reverse is true if the acceleration is downward. If the acceleration is pointing downward, and you can see here there's a little blue arrow also reminding us of that, what's happening is the elevator and the scale are actually accelerating out from underneath your feet. And so you feel less weight than you would if it were standing still. Now, as the acceleration downward gets bigger and bigger, eventually it'll get to little g, 9.8 or about 10 meters per second squared. Once that happens, you and the elevator and the bathroom scale are essentially all in free fall. Or you could imagine if the cable were to break, it would be the same thing. You would fall, the elevator would fall, the bathroom scale would fall. And just like the guy in the car in the last example, you would just basically be floating as you fell. Some people think that if an elevator were to fall, they could wait until the last minute and jump upwards just as the elevator hit, and that would save them. Well, obviously you can't do that because you're not going to be having gravity pull you down to the ground for you to leap off of. But even if you could, the whole thing, you, the elevator, and the scale would all be going very, very fast when you hit. Even if you could jump upward, you'd be jumping upward relative to the elevator floor, not to the ground. The total velocity, you'd still be going down very fast, and it would hurt a lot when you hit. Incidentally, real elevators, they have things to prevent that from happening. They have things that catch the elevator when they fall, and even if the elevator were to have a catastrophic system failure and fall all the way down to the bottom, they have something like essentially giant springs or something like airbags in a car. They're actually bags filled with oil, not with air, but they basically act as shock absorbers, and they decrease the acceleration of the elevator when it hits, so that you remember from our last lectures, if the time is increased, the force goes down. That's what happens in a real elevator shaft. If the elevator falls, there are things at the bottom to slow it down, to increase the time of impact when it hits, so that it's possible for people to fall in an elevator and survive it. Now, the force of gravity always points down towards the ground. The acceleration due to gravity is always accelerating things down to the ground. The force of gravity does not pull things left or right. It does not accelerate things to the left or right. It only accelerates them downward. And so if I have a ball and I just drop it, as it falls, it's going to go faster and faster because it's accelerating due to gravity. On the other hand, if I have a ball on a table and I give it just a kick so that it's got some velocity, it's not going to speed up because gravity doesn't pull side to side. Now, it may slow down because of friction, but before friction can really affect its velocity, it's basically going to move at a steady speed according to the law of inertia. Things want to keep the motion they have unless there's a force acting on them. So if friction is small, this guy's going to go for a long time and it's going to go at a steady speed. But if I drop it, it's going to accelerate because there is a force, the force of gravity, and every second its speed increases by 10 meters per second. Now, over on the right-hand side of the screen, we see a very famous picture of a very famous experiment illustrating the effect of projectile motion. Now, what they did was they have two balls, the red one and the yellow one in this picture, and at the same time they're released, but one of them is dropped straight down and the other one is given a little kick so that it starts out going sideways. But once they're released, they both are pulled down to the ground by gravity. And what they did was they basically used a strobe light, and so every time the light flashed, the image of where the ball was got stuck on the negative of the film camera. This is typically made with an old-timey camera that uses film. And so you can see at basically every flash of the strobe is like the tick of a clock, and you can see where the ball was at that time interval. And so what we see is that going down, the interval between where the ball is getting bigger and bigger as we expect, because we know that downward both balls are accelerating. And you can see these horizontal lines. What they show is look where this red ball is and where the yellow ball is. They're in the same spot. Look here where the red ball is and the yellow ball is. They're in the same spot. The downward motion is the same for both balls because both balls accelerate with little g. They both have the same amount of acceleration, and so downward they're going to go the same distance downward with each tick of the clock, or in this case each flash of the strobe light. Now, if you look at the yellow ball's side-to-side motion, each motion is the same distance over compared to the previous ball. And what that means is that this guy's basically going at a steady speed left to right, even as it's accelerating on the motion downward. And so you combine the left to right motion with the up and down motion, and you get this nice curved trajectory. And that's what most projectile motion looks like. You have this nice curved trajectory. Say that 10 times really fast. It's a little tricky. But anyway, if you've had algebra in high school, you might remember parabolas. The motion of a projectile is actually usually a parabola. And if that's a word that sounds like gibberish to you because you don't know what a parabola is, don't worry about it. You don't really need to know that. But what you do need to know is that the motion of the red ball is straight down just because it simply drops straight down. But the one that's kicked off at an angle or kicked off sideways is going to follow a curved path. And the key thing, though, is that they fall at the same rate. Even though one of them's moving side to side at the same time, they both fall at the same rate. And here we can see how these two motions work together. So in the first picture, we have horizontal motion with no gravity. So if I could turn gravity off and give it a kick sideways, it would move straight in a straight line. That's what Newton's first law tells us. If you give it a sideways motion, if there's no other forces, it's going to keep that sideways motion forever. Now, here's the vertical motion with gravity only, and you can see it's falling and it's also accelerating. The distance is getting bigger and bigger because it's going faster and faster. Now, if you combine those two motions, so after 1 second, say the ball is going to go over this far and it's going to drop down that far, you can see that that ball is here. And then the next ball is over a certain amount and down a certain amount. The next ball is over a certain amount, down a little bit further because it's accelerating downward. And so when you put all of those together, you can see the path of the ball. And this is kind of showing all of the figures together, that the side-to-side motion plus the up and down motion equals this curved path. Now we have an example problem. It says a ball of mass 1 kilogram rolls off a 1.25 meter high table and it hits the floor 3 meters from the base of the table. In other words, this ball is launched sideways off the table. It's going to fall 1.25 meters and it's going to travel sideways 3.0 meters, and at that point it hits the ground. And the question, part A, says, show that the ball takes 0.5 seconds to hit the floor. Well, that's pretty easy to do, actually, because here's the thing that you have to remember. When you have projectile motion, the side-to-side motion and the up and down motion are completely independent of one another. That means you can use the formulas you know for the side-to-side motion separate from the formulas you know for the left-to-right motion. So what's the formula we know for the distance something falls and how long it takes to fall? Because we want to find how long it takes to fall. So we know the distance. We know there's a formula that relates how far something falls to how long it takes to fall. Do you remember that formula? If not, it's the formula D equals 1/2 GT squared. And so hopefully that's familiar for you now. And so we can actually plug in some numbers because we know that the distance that it falls now, not that it's going side to side, the distance is 1.25 meters. That's the distance it falls. And that's equal to 1/2 times 10 meters per second squared times t squared. And when we simplify this, we want to get t squared by itself. And so we can multiply both sides by 2. And so if I multiply that side by 2, those will cancel. And I can multiply that side by 2, and I get 2.5 meters is equal to 10 meters per second squared t squared. And then to get, again, I still want to get t squared by itself. So I'm going to divide both sides by 10 meters per second squared. And so I'll divide this guy by 10 meters per second squared. And what I end up with, I get meters over meters cancels. And this is 1 over second squared. So when I do that, the second squareds come up to the top unit-wise. But the important thing is that you have 2.5 divided by 10, and that gives you 0.25 seconds squared is equal to, and over here the tens are going to cancel and leave you with t squared. And to get t by itself, not t squared but t, we simply take the square root of both sides, and when you take the square root of 0.25, you get 0.5. You take the square root of seconds squared, the squared goes away, you get seconds, and the squared goes away over here on the right, and so you end up with t equals to 0.5 seconds. And that is the answer for part A. Now we can look at part B. Now part B says, show that the ball leaves the table at 6 meters per second. Now we know that the formula for speed is equal to distance over time, and the horizontal distance is what we're talking about because we're talking about the horizontal velocity that the thing is launched with. And so the distance is 3 meters, and we're dividing by the time it takes to hit the ground, which in the last part of the problem we found was 0.5 seconds, and 3 divided by 0.5 gives us 6 meters over seconds. And of course, that's what we would expect for a speed or a velocity. And so that's the speed that the ball leaves the table with, 6 meters per second. And that's our answer. Now we're going to continue looking at projectile motion in the next part of the video lecture. We're going to look at part 2, and we'll also look at how satellites work, which is a really, really cool thing. So I'll see you in the next video.